Energy is the ability to do work. As we've learned earlier, work and energy are closely related, same units. The units are joules. For energy, any kind of energy, we'll use a capital J. There are different forms. There's nuclear energy, electromagnetic energy, light, X-rays, gamma rays. We'll study those second semester. But we're going to focus mostly on two forms of mechanical energy. Kinetic, which is energy associated with motion, things that are moving. And potential energy, energy stored or associated with position. And there are different types of potential. There's elastic potential energy, like when you stretch out a rubber band or a spring. Chemical potential energy, like in batteries, gasoline, food. We're not going to take a close look at those, but we will take a close look at gravitational potential energy, and I'll define that in a second. But let's go back and talk about kinetic energy in particular. There's an equation. Kinetic energy is equal to 1/2 times the mass times the velocity or speed of an object squared. So it's 1/2 mv squared. Where the kinetic energy, Ke, is in joules, the mass is in kilograms, and the speed or velocity is in meters per second. So as you can see here, velocity is very important with for kinetic energy. And I'll give you an example in a second, but like when you double the velocity of an object, you're increasing its kinetic energy greatly because you're squaring that factor. GPE, gravitational potential energy, is equal to m mass times the acceleration due to gravity times your height, mgh. The GPE is in joules, like any energy. The mass being in kilograms, little g is 9.8 meters per second squared, which we can round off to 10, and the height in meters. Here's a baseball with mass of 960 grams. Somehow there's a misprint there. That's 960 grams. And the ball's moving, it's a 90-mile-per-hour fastball. That's 40 meters per second. So let's do the calculations in metric units. The kinetic energy will be 1/2 mass times velocity squared. That's 1/2 mass times velocity squared. So the kinetic energy here is 1/2 that's 0.960 kilograms times 40 squared, 40 meters per second squared. If you do the math there, the kinetic energy comes out to be 768 joules. That same ball, though, thrown half as fast, say a knuckleball, the kinetic energy is going to be 1/2 times the same mass, 0.960, times 20 squared. So the kinetic energy in this case comes out to be 192 joules. One thing to notice here is that this second computation, compared to the first, is 4 times smaller. In other words, when something's moving half as fast, it has 1/4 of the energy, or we can switch it around. If it's moving twice as fast, like the fastball, 40 meters per second versus 20 meters per second, it has 4 times as much energy. Keep that in mind for future reference. Or here's another example. What if you triple the speed? If you went to 60 meters per second here, the ball would have 9 times as much energy as the original. Because when you triple the speed and square it, 3 squared is 9, your energy goes up by a factor of 9. One more example. Say your speed goes up by a factor of 5. Then your energy goes up by a factor of 25, because 5 squared is 25. This is only true for kinetic energy because you have a square of one of the factors in that equation. Alright, the GPE of a box sitting on a shelf is mass times G times H, which again, we'll take our 0 position as the floor, so we're doing all these problems with reference to the floor as being our 0 height or 0 GPE level. But we need to get the mass of this box. If you remember, weight equals m times g. The weight is given here as 7 newtons. The mass is unknown, but if we use our simple 10 for G, the mass comes out to be 0.7 kilograms. The GPE, therefore, is that mass, which is 0.7 kilograms, times 10 times the height from the floor of 3. And if you're looking carefully at this once again, what you may notice already, maybe you did, maybe you didn't, that this mg, which is the weight, we really kind of did an extra calculation there because that really is that same quantity right there. So GPE can be thought of as the weight times the height, or the force times the height, so to speak. Anyway, GPE in this case is 21 joules. All right, we have the law of conservation of energy, which states that energy cannot be created or destroyed, it can only be transformed. From one type to another. I'm going to have an example here, but also we'll be using some examples in class with bouncing balls that transfer from GPE to kinetic energy. But the roller coaster example below here is a very good mathematical example. We have a roller coaster on top of a hill. The hill is 32 meters tall. That's over 100 feet. And it's starting from rest, it's going to roll down. At the top of this hill, it has a GPE, gravitational potential energy. At the bottom of the hill, the roller coaster car will have a kinetic energy. And what's going to happen is the GPE is going to transfer to kinetic energy because of the law of conservation of energy. And we're going to ignore friction for now. What we want to do is calculate the GPE at the top of the hill. It's going to be mgh is the equation. So the GPE at the top is the mass of the car, which is 450 kilograms, the units are good, times G, 9.8 or 10, times the height from the ground, 32. So the GPE comes out to be, I believe, 144,000 joules. Now that's going to transfer into the kinetic energy of the car at the bottom. So the kinetic energy at the bottom will equal 1/2 mv squared at the bottom. But the kinetic energy at the bottom will be this 144,000 joules. So I'm going to plug that in for the kinetic energy. So I'm going to have 144,000 joules equals 1/2 times the mass, 450 kilograms, times v squared. If you do the math here, v comes out to be 25 meters per second, which is over 50 miles per hour, which is pretty fast in a roller coaster. Now, part B. The car is starting with a kinetic energy at the top and a GPE at the top, and it will have a new kinetic energy at the bottom. So what happens here is the GPE at the top plus the KE at the top will combine to then equal or transfer to the KE at the bottom. We already know that the GPE at the top is 144,000 joules. It's the same hill as before. I didn't mark that down, 32 meters. But there's also a kinetic energy at the top. The kinetic energy at the top is going to be 1/2 the mass of the car, 450, times its initial velocity. It's already moving, in this case, at 12 meters per second, and we have to square that. Don't forget to square that. That's a mistake that's made quite often. If we do the computation here, it's going to be 225 times 144. That comes out to be 32,000 joules of kinetic energy at the top. So what we'll say here, or what's commonly referred to now as the total mechanical energy, the TME, let me write that down, the total mechanical energy, the TME, at the top is the sum of those two. In other words, if I take the 144 plus the 32, the TME, 144,000 plus the 32,000, at the top, the total mechanical energy at the top is 176,000 joules. It's a combination of GPE and kinetic energy. Well, that's all going to transfer to the kinetic energy at the bottom. So the kinetic energy at the bottom will equal the 176,000 joules. In other words, 176,000 will equal 1/2 times the mass of the car, 450, times V squared, the V being at the bottom. It comes out in this case that V is 28 meters per second. That's in meters per second. So now we're approaching 60 miles per hour. So this is a very good example of conservation of energy, and we're assuming no frictional losses. Energy was not created or destroyed. It was transferred from, in the first case A, all GPE into kinetic energy. And in case B, a combination of kinetic energy and GP at the top to all kinetic energy at the bottom. Law of conservation of energy.